Okay. Good morning to everybody. The topic of my presentation is the energetic and geometric criteria for defining shear-deformable beam models. And okay. So my concern in dealing with this topic was the tentative to establish a connection between the three-dimensional well-known Sandvenant model and the one-dimensional beam model. Because I think that sometimes we cheat our students, since we continuously switch between 3D model, the Sandvenant model, and the 1D model, and probably students do not have completely clear when you are dealing with the 3D and the 1D model. And this problem is even more puzzling, because when you connect the deformed shape of the 3D model of the beam axis, the axis connecting the center of gravity, this deflection exactly coincides with the one you get from the 1D model, the Eulero-Bernoulli model, in which you discard shear effects, shear stresses. So the problem is it possible to guarantee a complete equivalence between the 3D model and the 1D model in such a way that you include also the effects of the shear stresses? And the outline of the presentation is such that we briefly, of course, recall the 3D and 1D beam models, and we recall the conditions of statical equivalence, and we briefly present the classical criteria for defining the 1D beam models. I mean the criteria that are usually exploited in the literature to guarantee that the deformation, the deflection of the beam model is equivalent to the 3D one according to an energetic or a kinematic approach. And then we prove that this can be arranged in such a way that you can, at the same moment, fulfill complete equivalence, both in terms of energetic approach and a kinematic one. So my objective is to introduce, to guarantee, to obtain a 1D model that is fully equivalent to the 3D one, the Sandvenant one, both from the energetic and the kinematic point of view. And we shall prove that this can be done, and this is successful. Okay. This is well-known Sandvenant model, one-dimensional beam model. You have the statical quantities, stress tensor, the internal forces, the kinematic quantities of the two models, the displacement field and the warping function, and the V function and the phi, so the deflection and the rotation of the beam axis in the 1D model. You have the constitutive law and the stiffnesses on the one-dimensional beam model. From the statical point of view, there is consistency between the solid model and the one-dimensional model in terms of internal stresses and internal forces. These are standard definitions that we usually teach to our students. So you have your extension, bending, shear, torsion, and we are applying the axial force at the generic point P on the section, at generic point F, and the shear force at the point P. And this will be particularly important because you will find, we will find that the equivalence of the two models include explicitly the position of the point P at which the transversal force T is applied. And so this is the position of these two forces are denoted by the vector Rf and Rp. This is these are the standard relationships that we use when presented the Semmenan model to relate the internal forces, the axial force and the shear forces to the force and the bending moment mb, the transversal force, the shear force T, and the bending moment mt. Well-known relationship. Please notice that the difficult part of this solution when expressing and evaluating the shear stresses in the section are the evaluation of these three harmonic functions. This is a scalar function associated with torsion. This is the warpage, the so-called warpage. There are two functions. It's a vector of two functions. These three functions are obtained by solving three Neumann problems over the section. So you have to solve preliminarily three Neumann problems over the section of your beam model. And of course, we are supposing that this preliminary stage has been accomplished and you know these three harmonic functions. Well, how can we derive the one model from the 1D model from the 3D one? As I told you, as you know, we have basically two criteria: the energetic criterion, the geometric criterion. In the first one, you evaluate the elastic energy, and you enforce that the displacement associated with shear stresses, both deriving from the shear force and from the torsion, gives you an energy that is equivalent to the one of the 3D model. We are not dealing with with displacement due to bending because this property is already accomplished. I mean, both in terms of energy and in terms of geometric quantities, in the 1D model and in the Semmenan model, you will get the same solution. This is not true. This does not hold for the shear stresses. And that's why in the literature, you find two different approaches that reflect in the definition of the so-called shear correction factors. And we have tried to reconcile these two approaches in order to get one expression of the shear correction factors that allows you to completely establish completely the equivalence between the 1D model and the 3D model. So, as I told you, we focus, of course, on the tau effects. You can establish the internal energy by writing a bilinear form in terms of these shear tensor, dE. E, of course, remembers of energetic, and we shall see, on the contrary, that we shall see that you have the same expression in terms of the geometric criterion in which you relate the displacement, the transverse displacement and the axial rotation to the applied force in terms of another tensor where G, of course, reminds of geometric. So if you make some computations and you divide the shear forces in the two addends due to the shear and torsion, you get this expression, and you can evaluate internal energy in this form. You can synthesize this expression by writing this 2x2 matrix, which is obtained in this way, in this form. Jg is the inertia tensor. Phi E is a tensor with, which depends upon the warpages of the function, and Cp is another tensor that explicitly accounts for the position Rp of the point at which the transversal force has been applied, and Rpsi is a vector related to the warpage function psi. Rt is the center of twist, it's defined in this way, where Sv is the static moment of the function associated with torsion. So basically in this expression you get both a contribution due to shear and torsion. On the contrary, we are again with the energetic criterion. You can express this, you can synthesize this expression by writing something of this kind, in which you have the energetic tangential flexibility tensor, I remind you, associated just with shear. And now we switch to the geometric criterion. Of course, in defining geometric criterion, we have the main problem of the Semmenan model, which is a model, as you well know, with no constraints at the end. So we have to establish in which way we want to establish the equivalence between a one-dimensional model, which is a cantilever, a clamp at the beginning, and at the Semmenan model. And in addition, we have to define the parameters that define the kinematics of the cross-section. And we have defined as these parameters, well, let us discuss the effects first of the constraints. This is the vector that gathers the displacement associated with the Semmenan solution. This is the rigid mode due to the fact that we have no constraints. And the condition of equivalence between the 3D models and 1D model is to establish in a weak form. That is, we enforce that this orthogonality condition between the displacement u at the initial section and this arbitrary stress vector that is an arbitrary stress field fulfilling the Semmenan's hypothesis. So this is our criterion for establishing the equivalence in terms of constraints on the 3D model. For the kinematic parameters, we get the transversal displacement is that associated with the position P at which the shearing force is applied, and the rotation, of course, is the rotation of the section with respect to the zeta axis, the longitudinal axis of the beam. Okay, so the shear, the displacement due to shear is the sum of the one associated with the bending stresses. This is the well-known formula, and for the cantilever. And the difficult part is the evaluation of this share, of this contribution due to the tau, the tangential stresses. And we can express this term in two different ways, depending on whether we adopt an energetic or a geometric approach. In the geometric approach, we have a formula that seems to be quite similar to the one we have derived from the energetic approach, but there is a certain difference between these vectors, this tensor, that, as you can see, depends on the warpage of the section, but explicitly depends upon some geometric properties, some constitutive properties, while the additional term looks like quite similar to the other one, and as a matter of fact is exactly the same, although written in a rather different form. So again, we can collect all these formulas by writing the final expression of the displacement due to shear, relating this to the forces, the two shearing force and the bending and the torsion, by means of this tensor that is a geometric quantity, which depends upon the tensors I showed you before. So let us now compare the two formulations, the two expressions of the energetic and geometric approach. Formally, you write the same expression. The real difference is in the definition of this tensor. You have the same structure of the formula, but here you have a tensor. Here you have another one, energetic, geometric. These two other tensors looks different, but as a matter of fact are similar, and they are compared here. Look at that. These are the expression of the phi E and the phi G. And as I told you, in this formula that is very elegant and symmetric, you get just the warpage function, and this is a geometric tensor. While in this other formula you get some geometrical quantities, and you get the constitutive parameters that in these other formulas are hidden in the expression of AP. So our main concern was to prove the equivalence of these two tensors, while the equivalence of these other two is rather easy, are trivial algebraic manipulations. The real problem was to establish the equivalence of these two tensors, and we succeeded to do that, and actually we decided to denote by a symbol phi, independent of your energetic and geometric approach. So a unique tensor can be defined that has both an energetic and a kinematic meaning, and in this way we can establish a complete equivalence between the 3D model and the 1D model. And in particular, another source, in our opinion, my opinion, of confusion when trying to work with 3D models and 1D model is the concept of center of shear, which produces confusion with the center of torsion. The center of shear is well defined in the M&M model, in the 3D model, as the point of the cross-section where the shear force must be applied in order to induce no torsional effects. But this problem is limited, this definition of the center of shear is limited to the M&M model. It has to a model which has no constraints and the ends. When you want to establish the equivalence of this model, of these important, significant models, with the one-dimensional model in which you are obliged to include the constraints, you have to make reference to just one point, which is the center of torsion or the center of twist, which is a point univocally defined. Also when you have constraints at the ends. And actually, when we enforce in our formulation the independence, the orthogonality of the shearing and torsional effects, you have to enforce this condition that establishes basically that the so-called, what is usually called the center of shear in the energetic and in the geometric approach, actually does coincide with the center of torsion. So in our opinion, to avoid confusion, it's necessary to make reference to one point, univocally defined point, the center of torsion or the center of twist. And of course, this results allows you to overcome the traditional energetic kinematic dualism in the definition of the center of shear. And we suppose that not by chance you find in the literature two different definitions of the center of shear. The one which is based on the energy approach, which is usually credited to Treffs, and the one which is based on the vanishing of the average rotation, which is credited to Goodyear, and is at least 70 years old. Actually, these two definitions have no reason to exist. There is just one point to consider, which is the center of twist. And of course, this dualism, the geometric and the kinematic dualism, influences also the definition of the shear flexibility of the shear tensor. You have the definition by Renton, which is an energetic definition, and you have the geometric one, which is due to Dong, and gives you a non-symmetric tensor of the shear flexibility, which is something that looks quite strange. On the contrary, our tensor is clearly symmetric and overcomes this problem. And as I told you, however, this depends explicitly on the point of application of the point P at which you apply the shearing force. So, as a conclusion, a 1D model can be derived from Saint-Venant model by following an energetic or a geometric one. Of course, the consistency between these two criteria is strictly related to the assumption which we have made in defining the geometric model and the orthogonality between the displacement at the first section of the beam and the stress distribution due to Saint-Venant. And of course, you can define additional geometric models if you change this assumption. But independently on the kind of geometric assumption you get, you have a scalar quantity which, to make Professor Dell'Isola happy, has to be always respected, which is energy. So the energy of the two models have to be the same. And that's why we suppose that we assume that the geometric model and the comparison between the geometric model and the energetic one can be exploited, has to be exploited to validate the legitimacy of the kinematic assumption. So you have to take kinematic assumption in order to guarantee the equivalence of the energy between the 3D model and the 1D model. Thank you very much for this.
Yes, very nice. And what you did, in fact, was to get one-dimensional model which takes into account the Saint-Venant kinematics.
Yeah.
So when you think of one-dimensional model, it's nothing which has to do with Kirchhoff, Timoshenko, Reisner. Okay,
it's Saint-Venant.
Yes,
Stop.
But so you have a clear depiction of the geometrical factors and like
But you are teaching this to students?
Yes, the first part, not this one, because I have no time. I make this in the PhD.
It's still embarrassing to teach to the student the Kirchhoff rod and the Saint-Venant beam, because they are two different objects and they completely go crazy. And because they say, why I have to get the bending moment taken from Kirchhoff into the Saint-Venant when I say that one is one-dimensional and the other is a two-dimensional model?
Yes.
That's why. This is a neat approach.
That's why we tried this other approach, because that puzzled me when I was a student. So I had this fly that.
Luciano, when I started to work with Di Carlo, he gave me a book by Capuzzo, the work of Capuzzo, and I read one of the papers of Capuzzo in which probably this idea was at the very beginning. You don't know that paper?
I don't know. I read the papers.
This is much clearer. Really ended.
I read the papers on the thin-walled sections by Capuzzo. There are another source of confusion, extreme confusion in thin-walled sections, not the papers by Capuzzo. In general, in the literature, is something that really upsets me. Really upsets.
I want to ask you if you can share his point of view about the question of the shear center. You have the forces or cables and you have deformations, and so you have to construct constitutive relationship. So you can ask the question, is possible to obtain some constitutive relations for shear and couple in which there is no coupling? So in this sense, it is just a representation of the constitutive behavior of the solid. And is the same way as saying that the normal force in the Semmelweis theory is applied at the center of the section. And in this case, the normal force is uncoupled with the moment, with the coupled moment. But if you define the normal force as an integral which is applied not to this product, at the point, you have a coupling between the normal force and the bending moment.
The static moment.
In this case, the coupling between the shear and torsion could be seen as just a matter of constitutive representation. Do you agree with this point of view?
Not completely. I mean, because in my personal theoretical framework, now in my mind, and I try to, of course, teach this to the students, you have two different problems, bending, and you have a special point, the center of gravity, and shear, and you have another special point with the center of twist. So this is, in my opinion, much clearer. You have these 2 points that govern these 2 behaviors, and you can do everything. Another source of confusion is, as you well know, that the center of shear depends upon the constitutive properties of the material. The center of twist, no. So it is really a geometric quantity as the center of gravity. And this source of confusion becomes greater when you read the literature, in which you always find a confusion between the definition and the use of the term center of shear and center of torsion. And to make things even more confusing is that when you have a thin-walled section, the 2 points tend to coincide, or when the Poisson ratio is 0. So I think that in my opinion, the concept of center of shear is an elegant way to say that shear and torsion can be divided, but you have to completely discard the concept of center of shear. I want to make reference to the center of twist because it's a point, it's a geometric quantity, univocally defined, depends only on the shape of the section, not on the elastic properties of the material. In my opinion, of course.
Okay, we can discuss now.
We shall.
Yes, but what about the shear correction factor then?
Yeah, the shear correction factor has to be defined according to this formula. These are in this expression. This is the shear correction factor, because they appear in this you see? These are displacements. This is the tensor that relates the forces applied to the section with the displacement. And this is the tensor I showed you before. Inside this, there is the center of twist. So this is a univocally defined section, the tensor that depends just upon the geometric quantities, the property of the section and the length of the beam. That's all. I have no problem with the elastic properties. It's something strange that a point depends upon the elastic properties of the material and the points change according to the material. It's something that is not realistic.
And also not condition, by the way.
So you can use for whatever kind of section. We have done this. We have also compared the results of our 1D model with a three-dimensional model, finite element model with millions of degrees of freedom, and the work seems, and the thing seems to work. The results are quite similar.